barked. What's that?
What?
Scotty barked. That's the protector that I have on my registry monitor. It checks to make sure that that nothing is changing my registry without my permission. And every time something tries to change the registry, Scotty barks. He goes, "Ruff!" And that's your way of saying, "Alert! Alert! Something bad is going on." It's okay because he'll block it until I give permission. So I'll do what Scotty later. All right. So here's a question. Let's take a look at another series. Let's see if we can figure out if it converges or diverges. Let's take a look at this series. Let's take a look at, and this is in the book, sigma I equals 1 to infinity of 1 over k times, they want k minus, what do they do? Yep, they do k times k plus 1. Nice. So let's see if we can figure out whether this converges or diverges, shall we? Can we give this a go? What do you think, V? Should we make a stab at it? Okay, so V, what are my first couple of terms? What's my first term? Now, all I'm doing right now is, this is a series, I just want to write out the sequence. Just want to do the sequence.
Like a one?
No, you got to plug 1 in and then 2 and then 3. There's nothing to make up. Plug it into the formula.
So that's 1.
So I put a 1 there and a 1 there and I get
A half.
a half.
Oh my goodness.
What's a sub 2?
Wait. 1/6?
Yeah, it's 1/6. It's 2 and 3. 1/6. What's a sub 3?
Wait.
12.
1/12?
1/12. What's next?
1/20.
Okay, it's going to be 4 and 5, 1/20. Good. So those are, now we're just going to do some partial sums. So the question is, if I continue this out,
130.
this is going to be 1 over k times k plus 1. The question is, if I add up this sequence and make it into a series, and here it is a series, does this converge or diverge? Now, by the way, the reason they chose this particular series is because we can pull some more parlor tricks on it and get it to do what we want. It is the case that we're going to come up with tests for convergence and divergence in the next several chapters. Right now, we can manipulate this to figure it out without needing any of those specialty tricks. So here's what we do. Who would like to decompose this for me? That's a nice face, Em. We are gonna do fraction decomposition on this.
Okay.
So I have 1 over
K.
k times k plus 1. Right?
A over K.
Okay, this equals a over k plus b over k plus 1. So M, oh yeah, M's going right. Okay, so this equals what, M?
A times k plus 1
A times k plus 1
plus b.
plus bk over k times k plus 1. So 1 has to equal ak plus a plus bk. Hoity-toity. So 1 has to equal that. So M, what does A equal? I like calling you M because it sounds like a variable name. It confuses everybody in video land. So Emily, what does A equal?
No, I don't know.
Okay, so
Take a look. Take a look. What is my only constant term?
1.
1. Woo, good girl. And where is it? Good guess. Which of these is my constant term?
Wait, what? Could we not do that and just do the?
You want to do it the other way?
yeah.
Okie dokie.
What?
Okay, that's all right. No, it's okay. She wants to plug in numbers. It works. So M, plug in a number. What do you want to plug in?
Minus 1.
Okay, so if I plug in -1 for k, what's that going to do? It's going to eliminate this term, and I get a -1 here. So negative b equals 1. So I have negative b equals 1, so what's b equal?
Yeah.
B equals -1. Okay, so what number do you want to plug in next?
0.
I'm going to plug in 0. If I plug in 0 for k here, that eliminates this term. If I put this here, I get a equals 1. So a equals 1. So a equals 1, b equals -1. So now let's rewrite our sigma notation. May I erase this? Y'all know how to do decomposition, okie dokie. This is the part that I want, so I'll leave it for a second. Okay, so I can rewrite this sigma. I can rewrite this sigma as I equals 1 to infinity of 1 over k minus, I'll just move the minus sign down here, 1 over k plus 1. So now let's write out the terms again, shall we? So let's do this, but instead of writing them out like this, let's write them out in our new decompositional expanded form. What happens when I put in 1 here and here? Okay, I get 1 minus a half. That's my a sub 1 term. Okay, so what's my a sub 2 term? I'm going to put 2 in, so what do I get?
A half minus a third.
I get a half minus a third. That's a sub 2. Okay, so what's my a sub 3 term?
A third minus a fourth.
1/3 minus 1/4. That's a sub 3. Let's just do one more to make sure we're all getting this. What's a sub 4?
Fourth minus a fifth.
That's going to be 1/4 minus 1/5. Now, this is an infinite series, so I don't have to keep it grouped. I just put parentheses around this to make it easy to see which equals which term, right? Do I need the parentheses? Oh, I don't need the parentheses. Let's get rid of the parentheses.
Oh, you can.
Ooh, much easier with the parentheses off. I'm here too. You got that aha moment. I heard it all the way up here. Mirror 2, what is the aha moment that you just had?
You can cancel a lot of them.
Oh, look! They
All of them.
cancel. They cancel.
Except one.
They cancel. Well, the only reason I don't have the end one is because I was too lazy to write the a sub 6
All
term.
of them but one.
So if this goes on infinitely, they have infinite cancellation. What am I left with? So what does this series equal?
One, so it does convert.
That series converges to 1. Now here's something to play with just for fun. This is where infinite series gets fascinating, right? We said that this sigma notation equals 1, right? What else did we just say equals 1? What other sigma did we do that equals 1?
The half, third.
Yeah,
fourth,
this.
half, 48.
So it is the case that sigma I equals 1 to infinity of 1 over k times k plus 1 equals whoop! But the terms are so different. It adds up to the same thing. And this is why infinite series is
Awesome.
cool.
Cool.
Because, and why do I show this to you? The book doesn't show this to you, it doesn't make this connection. I want you to make the connection. Why? Because the point is, there are lots of infinite series that add up to 1. Well, why is that good news? It's good news because that means if a particular representation of an infinite series doesn't work, maybe we can find a different one that does. If we have an infinite series that we have, I mean, stop and think for a minute. Do we have a formula for calculating this? Yes. Do we have a formula for calculating this? Well, we used a parlor trick. Sort of. This is actually easier to work with because we have formulas for this kind of stuff. The same thing happens in infinite series all the time. You have an infinite series and you don't like it. All right, find a different one. Can you do that? Yeah. And we'll learn ways at the end of the chapter to construct our own infinite series. And if we don't like an infinite series, maybe the infinite series converges, but it converges too slowly. So we have to take like 100 terms to get the, we'd have to add up 100 terms in order to get the accuracy we want. All right, so we'll change the infinite series into something else and find one that converges faster, that makes us happier faster, because now we only have to add up 7 or 8 terms. That's what's cool about infinite series. Are we all good? So if you look, we covered 592, 593, 594, and 595. So now take a peek at, we're on the bottom of 596, a divergent geometric series. And do you see that? By the way, this book uses, the other thing that this book does quite differently, well, not most, a lot of books use I as the index for their infinite series. Some books use K. I'm in the habit of using I down here. The book is in the habit of using K. The index doesn't matter as long as things are written properly in here. So see, like here, if I have I, this is really written incorrectly. This should be I and I.
That one I was wondering.
Yeah.
And see, I put N here. It's not 2 to the N, that's 2 to the I, if I is my index. Well, if you had a question, you should have said something. Now, people in video land that only watch the first 20 minutes will be confused. So you do watch your index and your letters. Just make sure they're consistent, but use any letter you want. Okay. What else do we have? Oh, yeah. Fun.